let's continue from where we left it. So I'll now discuss another sort of production mechanism for dark matter, which entails in part what we already discussed, thermal freeze out, but before that it entails another part, asymmetry generation. So I will be talking about asymmetric dark matter. So first, what is the motivation for asymmetric dark matter? The motivation is basically, or part of the motivation is in this picture. If you look at this picture, you observe that the density of dark matter is about 5 times as much as the density of ordinary matter. And the question is, why are these two densities so similar? Now, of course, first you may say, well, a factor of 5 is not a small number. I mean, for collider physics, a factor of 5 is a huge number, right? So why am I even saying that the two densities are similar? Well, for cosmological problems, a factor of 5 is a small number in the sense that if the mechanisms that produced the relic densities of ordinary matter and dark matter were completely unrelated, if they are completely unrelated, then we expect that the resulting densities would differ by many orders of magnitude, not just by a factor of 5, right? The fact that it is, the two densities are of the same order suggests that there may be a connection between the two production mechanisms. All right, if we are to entertain this possibility, then we should probably first have a closer look at what happens with ordinary matter. We know that ordinary matter has 4 stable particles, the protons, the electrons, the photons, and the neutrinos, or at least the lightest neutrino. We know that protons make up most of the ordinary matter in our universe. And we also know that there are essentially only protons and no significant amount of antiprotons today in the universe. We know this in 2 ways. We know this observationally because there is a negligible, because there is no evidence for antimatter in cosmic rays. Everything we see is consistent with secondary production of antimatter. But we also understand this theoretically. The reason we understand it theoretically is actually what we discussed in the previous hour. The annihilation cross-section of protons with antiprotons is very large. And so if there were no excess of matter over antimatter, this excess is something that we call an asymmetry. If there were no excess, then the protons and the antiprotons would destroy each other very efficiently, and there wouldn't be enough left today. The density of ordinary matter would be far less, orders of magnitude less than what we observe, right? So therefore, we conclude that there must be an excess of ordinary matter over ordinary antimatter, and that the antiparticles of ordinary matter, the ordinary antiparticles, annihilated in the early universe with an equal number of particles, right? And what is left today is this part. Okay, so the idea behind asymmetric dark matter is that something similar happens with dark matter itself. That the relic density of dark matter is itself due to an excess of dark particles over dark antiparticles. And that perhaps this excess, this dark asymmetry, was dynamically related in the early universe to the ordinary matter asymmetry by high energy processes that occurred in the high energy environment of the early universe. Now today, in order to be consistent with all observations, the dark and the ordinary matter asymmetries must be conserved separately. Otherwise, we would be in danger of converting into dark matter, right? But we don't, luckily. Okay, so this is the idea behind asymmetric dark matter, but in fact, the middle part of this scenario, this over here, which was also was the motivation I gave, is actually not necessary. Dark matter may very well be asymmetric, and the asymmetry it has, it may have nothing to do with the asymmetry of ordinary matter. It may just, dark matter may just be asymmetric because it likes being so. So we should discuss asymmetric dark matter in a more general setting. So what do we need to have a successful asymmetric dark matter scenario? Well, we need on one hand a low energy theory that will contains on one hand the standard model, which has the ordinary baryon number symmetry. And our low energy interactions should also have a dark sector that possesses another global U1 symmetry, a dark global U1 symmetry, the dark baryon number. that ensures that the stability of the dark matter and the asymmetry in the dark sector. Moreover, we want the low energy interactions of the dark sector to be such that the symmetric part of dark matter annihilates very efficiently. And one important question here is how efficient this annihilation, how efficient does it have to be, right? So we'll try to answer this question later. Now, if we also aspire to connect the dark matter and the ordinary matter asymmetries, if we aspire to establish a relation between the densities of these two components, then we must have some high energy interactions which create these asymmetries, the two asymmetries of the asymmetry of dark matter and the asymmetry of ordinary matter, and they do so in a correlated way. So we must violate, to create an asymmetry, as I'll discuss this in a slide or two, we must violate the conserved symmetries of the low energy interactions, but to create related asymmetries, we have to do that in a correlated way. So this sketch is essentially the same thing. So in this sort of scenario, the order of events, the cosmological order of events is this one. We imagine that at very high temperatures, an asymmetry is generated, and in the dark sector, or it is, or in the standard model, and it is shared with the dark sector. Typically, the asymmetry is generated in not necessarily in dark matter itself or in ordinary matter itself. It can be generated or it can be carried by some heavy degrees of freedom, right? These heavy degrees of freedom can then decay via interactions which preserve the dark baryon number and the ordinary baryon number. These asymmetries can decay, cascade down into the lightest particles. And for the case of dark matter, this would be, well, the lightest dark baryon, dark matter itself. And eventually, after all of the asymmetry, the baryonic asymmetry has cascaded down to dark matter, we need, as I said, we need an interaction which will annihilate the symmetric component of dark matter. Why do we need to annihilate the symmetric component of dark matter? For two reasons. Because if we don't, we may overproduce dark matter. We saw in the previous hour that if dark matter doesn't annihilate efficiently enough, then we would have too much left today. If it has thermalized in the early universe and doesn't annihilate efficiently, then we have too much left today, right? So the same will happen here. And in addition, you know, if we aspire again to connect the densities of ordinary matter and dark matter, then by relating the asymmetries, we are doing just half of the job. We haven't related the densities if we do not eliminate the symmetric part, right? All right, so I will talk a little bit more about these two issues. How do we generate an asymmetry? Well, this is a nice piece of physics that was explained to us by Sakharov back in the 1960s. To generate an asymmetry, an excess of matter over antimatter, we need three conditions. The first condition is the most obvious one. We need some interactions which violate the U1 symmetry that exists in the low energy interactions. Only if we have interactions that violate the baryon number, we can make a net baryon number. Otherwise, we will always have a zero baryon number if we start from zero, right? So we need interactions that violate the symmetry. These interactions should also violate CP. Why is that? Because for every interaction which violates the baryon number by a certain amount, then there is the CP conjugate of this interaction which violates the baryon number by the opposite amount. Now, if CP is conserved, these two interactions happen at the same rate, and therefore whatever we create, we destroy, and we do not get a net baryon number. And the third condition we need is that these interactions at some point occur out of equilibrium. Why is this? Because as we saw in the previous hour, in equilibrium, every interaction and its inverse happen at the same rate, right? Remember the principle of detailed balance. So if these interactions, the B and CP violating interactions happen in equilibrium, then whatever we create, again, we will be destroying it. We get no net baryon number. And therefore, we need these baryon and CP violating interactions to occur at some point out of equilibrium. After we generate a net baryon number, what has to happen is that these baryon-violating interactions have to cease to be effective in the universe, right? Because if they keep being effective, then they will destroy what they created, right? So in the low energy environment of the early universe, these B-violating interactions have to be inefficient. So this is how you generate an asymmetry. These are just the conditions you need. This can be implemented in various particle physics models in different ways. I will not get into that. But what I want to now discuss is the second part of this mechanism, which is freeze out. So assuming now we have created a particle-antiparticle asymmetry early on, and perhaps we have related the dark asymmetry with the ordinary matter asymmetry, what happens next? We're now at the stage where all of the excess, or all of the baryon number, net dark baryon number, has cascaded down to the dark matter particles, the lightest particles charged under the dark baryon number. So what happens? Well, the dark baryons and the dark antibaryons will be annihilating, right? How do we describe freeze out in this case? Well, in this case, we have to keep track of the densities of the dark particles and the antiparticles separately, right? We cannot equate them as we did before. So now we have two Boltzmann equations, and we have two separate densities. While the annihilations are in equilibrium, dark matter will have this equilibrium density. The equilibrium density will be different for particles and antiparticles. And what makes it different is this chemical potential, this mu over here, which should be in equilibrium opposite for particles and antiparticles. Remember that from thermodynamics that chemical potential is something that is associated with conserved numbers, right? So here we have a conserved number, and therefore we need to have a chemical potential. All right, so we want to solve this system of equations under the assumption that we have a conserved asymmetry. Our asymmetry is the number of dark matter particles minus antiparticles divided conveniently by the entropy density of the universe, such that this stays constant as the universe expands, right? So we do the trick we did before with the comoving number density. Now we have the comoving number density of particles minus the comoving number density of antiparticles, right? And this quantity is conserved. For comparison, this quantity for ordinary matter is of the order of 10 to the minus 10, right? So it's something that is measured. Okay, so this on one hand is conserved, and on the other hand, what we need to compute, what we need to find out, is how efficiently the antiparticles will be annihilated. So we want to compute this ratio of dark antiparticles over dark particles. This will depend on time. Early on, it may be quite large, so of order 1, so we may have about the same, very similar numbers. Because we have a lot of particles and a lot of antiparticles with a small asymmetry, right? And as the universe expands, what will happen is that the annihilations will destroy the dark antiparticles. So we want to compute this using the Boltzmann equations and find the late time value of this ratio. So it is a simple exercise to convert these two equations into an equation that gives us R of t. And what we expect is that if the annihilation cross-section is large enough, to be seen how large enough it has to be, if the annihilation cross-section is large enough, then the dark antiparticles will be efficiently annihilated away, and we will get this R factor to be much smaller than 1. If, on the other hand, the annihilation cross-section is not very large, then we will not annihilate efficiently the antiparticles, and we will have a dark matter that is almost symmetric. So here is the result. Here is the late time ratio of antiparticles over particles versus the annihilation cross-section normalized to, remember, to the annihilation cross-section for symmetric dark matter, to what we computed before, this canonical annihilation cross-section that we called before, right? And what you see here, and from this formula, is that this ratio of dark antiparticles to particles at late times is actually, decreases actually exponentially with the cross-section. So even if I have a cross-section that is only slightly bigger than the canonical annihilation cross-section, than the annihilation cross-section for symmetric dark matter, if I have an annihilation cross-section that is only like a factor of 2 larger than this over here, the annihilation of the dark antiparticles is actually very efficient. I already get an R factor that is much smaller than 1, and I essentially have very highly asymmetric dark matter. Why is this important? Well, it tells us that, first of all, asymmetric dark matter can be WIMPs, right? Provided that I have a U1 symmetry at low energies, the WIMP annihilation cross-section is actually sufficient to give you highly asymmetric dark matter, right? And more generally, this computation tells us what sort of couplings we are allowed or we should try to have in a theory of asymmetric dark matter to have a viable asymmetric dark matter model. Right? Now, the other thing that this reminds us is that the annihilation cross-section of asymmetric dark matter doesn't have to be a particular value. It has to be higher than a particular value. It has to be higher than what you need for symmetric dark matter. But any value larger than that is OK, because you cannot destroy the excess of particles over antiparticles. Right? In that sense, asymmetric dark matter spans a much larger low energy parameter space than symmetric dark matter, which sets the annihilation cross-section to a specific value. Right? All right, so now the asymmetric dark matter idea is not new. There have been models from very old times, starting with Technicolor models back in the 80s and more recently in 2000s. Mirror dark matter models which postulate that the dark sector is an exact copy, or maybe not exact, but almost, of the standard model sector. In order to make this scenario viable, it's important to note that the dark sector has to have a different cosmology. Right? Another interesting scenario is cubules. This is also an asymmetric dark matter scenario. Cubules are solitonic dark matter. The difference is that cubules are non-thermal, entirely non-thermal, so the second part of what I just described doesn't apply for cubules. And more recently, in recent years, there have been a lot of models of asymmetric dark matter where asymmetric dark matter is either WIMPs or it resides in various hidden sectors. To have asymmetric WIMP dark matter, that's a bit more difficult than have it in a hidden sector, simply because there are many more constraints on WIMP dark matter in general, right? So most asymmetric dark matter models reside in a hidden sector.
Excuse me. Yeah. So what do you mean by a different cosmology?
So the cosmology of ordinary... Right. Good point. So what do I mean in the case of mirror dark matter with the mirror sector having a different cosmology? So the cosmology of ordinary matter contains many events that are important for the phenomenology of dark matter today, including not only just the annihilations, the freeze out of protons, or the asymmetry generation, but it also includes recombination, the formation of atoms. It includes nucleosynthesis. And all of these things affect how dark matter behaves today, how ordinary matter behaves today, right? Now, if you take a sector, a dark sector, which in terms of particle physics is exactly the same with the standard model, but cosmologically is at a little bit different temperature, then the result you get from calculating recombination in the early universe or nucleosynthesis is very different, right? And therefore, the phenomenology of dark matter will be different today, even if it belongs to a hidden sector that is a mirror copy of the ordinary sector. If this is the case, then I should say that the cosmology has to be different because dark matter has to behave differently than ordinary matter today, because among else we know that ordinary matter is dissipative, right? And we know that dark matter is not dissipative. Dark matter does not collapse, or at least not the entire, not all of dark matter, it does not collapse into disks. So So the way you ensure this is by having a different cosmology, which means different phenomenology today. So different rates of formation of hydrogen and of nuclei. It's complicated. It's not something. All right. So let me try to go with you through the exercise of building an asymmetric dark matter model with the ingredients we described before. We'll build perhaps half of it, not all of it. So what I will do here, it will be a very simple asymmetric dark matter model. So we have on one hand the gauge group of the standard model. And we said before that the ingredients we need, one ingredient is that we need dark matter to annihilate efficiently at late times. One of the simplest ways to do that is to say that dark matter couples to a dark U1 force. Maybe you can also choose another more complicated dark gauge group, but it will be more complicated. Or you can also have dark matter coupled to scalar force mediators, but that is not necessarily simpler. Okay, so I will assume that dark matter couples, I have a dark sector with a dark U1 gauge force. And I will also introduce another U1 gauge factor, which will be a generalization of the ordinary B minus L. This gauge force will couple as B minus L for the standard model particles, and it will also couple to the dark sector particles. Right? And the reason I want to do that is because I want to relate the asymmetries of the dark and the ordinary matter. Okay, now the assumptions here are that, I want eventually to have asymmetric dark matter, and I want it to be coupled to a dark U1 force, this U1D. Well, automatically from this you conclude, you see that if dark matter is just one species, I would have a net dark gauge charge in our universe. This cannot be true because of gauge invariance. Gauge invariance ensures the dark electric charge neutrality of the universe. And therefore, I immediately conclude that I must have at least two species, two dark species charged under this U1D that are both asymmetric and whose net charges cancel each other. So this is analogous to ordinary protons and ordinary electrons, right? If I only had an asymmetric population of ordinary protons, I would have a net electric charge in the universe. But this cannot be the case. So electrons are also asymmetric, and they compensate the electric charge of the protons, right? So similarly here, I will have dark protons and dark electrons. The difference with the standard model will be that these particles can be elementary in the simplest implementation, right? I don't have to have dark QCD. All right, so these particles will have charge 1 and minus 1 under the dark U1D. And I will assign also a baryonic charge of minus 2 to the dark proton, just because I like to do so. Right? Under these charge assignments, you can very easily see that the only interactions I can write down that are renormalizable and consistent with the gauge symmetries I have postulated are these interactions. So I have the standard model on one hand, the kinetic term for the U1D. I should have written a kinetic term for this one as well. And I have the dark fermions, which have masses. They couple to the gauge interactions, but there is no other interaction I can write that couples these two particles to each other, because they carry this U1D charge, but they also, one of them carries dark baryon number, the other one doesn't, right? It carries baryon number, I should say. Okay, so these are the only interactions I can write down with, at low energies with a small asterisk, I'll explain in a minute. And so from this, it is trivial to see that my Lagrangian has an accidental global dark baryon number symmetry, right? Which essentially coincides with the gauged B number in the dark sector. So what I have achieved here is that my low energy interactions have on one hand the global B minus L of the standard model, and on the other hand a global dark baryon number in the dark sector, which is exactly what I wanted. under these charge assignments, I can also start writing down non-renormalizable operators. So for example, I can write down this operator, which couples ordinary baryons to the dark particles. And what you can see from here is that this interaction, which is gauge invariant, preserves one linear combination of the global symmetries, the global baryon numbers, but violates the other combination. Why is this interesting? Because I can use this operator to create correlated asymmetries in the two sectors. You can do that in different ways. You can do it, you can supersymmetrize this model and do this by the Affleck-Dine mechanism, or you can UV complete this operator and have heavy particles decaying into dark fermions and standard model fermions and creating correlated asymmetries. You can do this in different ways. Of course, you need to elaborate on this model. But this is basically what you need to build an asymmetric dark matter model. In this model, and to go back to the discussion of having operators that connect dark sectors and the standard model, you're actually allowed to write down, there is one more renormalizable operator that is also gauge invariant, and it's the so-called kinetic mixing of the dark U1 factor, this one, with a hypercharge. You know that for U1 gauge symmetries, this F factor is gauge invariant by itself. For non-abelian symmetries, this doesn't hold. So for U1 symmetries, I can have mixing via this term at the renormalizable level. Right? So this is a portal operator. It is not necessarily suppressed by any large, it's a renormalizable operator. It's not suppressed by any high mass scale. But of course, the coupling is constrained to be small enough so that everything is consistent with observations, or the lack of observations. Right? Okay, so part of why I'm interested, I did this exercise is not just to model build, but in fact to now wonder how the phenomenology of asymmetric dark matter looks like. So here I have two dark species. Remember, I did not ask to have two dark species. I just said that I have a dark U1 force, and the dark U1 force and the symmetry immediately led to the conclusion that I have two dark species. I cannot avoid it, right? So what will happen in the universe? Well, early on, after the asymmetry is generated, and after the annihilations destroy the symmetric part of dark matter, both of the dark protons and the dark electrons, what will happen is that the dark protons and the dark electrons will get together and form dark hydrogen atoms. Right? This will happen at a temperature of about the binding energy of the dark atoms. So I will have dark recombination. I can sort of calculate how efficient this recombination is. And what is important to note here is that the residual ionization fraction is something that depends on the coupling. The larger the coupling is in the dark sector, the more efficient recombination is. Right? The larger the coupling is, the smaller the ionization fraction is at late times. Why is this important? Because this affects the phenomenology of dark matter today. So first of all, I will have multi-component dark matter. I will have ions and I will have atoms. And in terms of self-interactions inside halos today, I will have collisions that will involve ions or atoms and ions. Right? These collisions will have different cross-sections. And in particular, because they're mediated by a light force carrier, they will have a velocity dependence and will be different for ion-ion and atom-atom collisions or atom-ion collisions. So I immediately have a complex scenario, although I started from two very simple requirements. Right? I started from the requirement of asymmetry and the dark U1 force. I didn't want to complicate things, but this is what comes out from consistency. Right? And what is important to remember and to realize here is that there is an interplay between cosmology and particle physics. If the coupling in the dark sector, the dark gauge coupling, is small, then recombination will be inefficient, and dark matter will be mostly ionized today. you know that ionized matter scatters off efficiently, but on the other hand, the scattering cross-section is proportional to the coupling squared. So if the coupling is small, then, well, the scattering may not be too strong, right? As the coupling increases, the scattering cross-section, the self-interactions of dark matter inside halos increase. But if the coupling is too large, then what will happen is that recombination will become efficient in the early universe, which means that dark matter forms neutral atoms, which then screen the interaction. This is important to remember, that the early universe always regulates the interactions of dark matter, the manifestations of dark matter today. Because the early universe was a dense environment, if dark matter has some interaction that is very efficient, very strong, then the early universe will do something to regulate it. This is a way that the early universe does that here, and the formation of bound states in particular. So for direct detection, again, I will have a similar interplay when it comes to the coupling of dark matter. The direct detection may proceed due to this kinetic mixing between the hypercharge and the dark U1 gauge boson. Right? The indirect detection is quite interesting. Again, we may have indirect detection signals because of the kinetic mixing. So what we may expect is that we have annihilations of dark matter, the dark protons in particular, with the dark antiprotons. Of course, we said that dark matter is asymmetric, so we do not have very many dark antiprotons. So certainly, these annihilations are very suppressed by the asymmetry of dark matter. Nevertheless, there may still be some residual dark antimatter and may give rise to these annihilations. These annihilations will produce dark sector particles, dark photons, which then, if they are massive, light but massive, then they can decay via kinetic mixing into standard model fermions. Right? So this is how you can get indirect detection signals. Now again, this process will be very suppressed for asymmetric dark matter or for highly asymmetric dark matter on one hand. On the other hand, because this interaction is mediated by a light force carrier, the dark photon, it is actually Sommerfeld enhanced, which is something we'll talk about later. And so it turns out, if you do the calculation, that this annihilation rate can be somewhat significant even if the dark asymmetry, this R factor we calculated before, the ratio of dark antiparticles to particles at late times, even if that is fairly small, you can still have some significant annihilation signals. Now, besides this, there is actually another novel, more novel sort of signature, which is radiative level transitions. There can be many different kinds of this. Now, in our particular example, you can have the residual ionized component of dark matter, so the free protons and the dark protons and the free dark electrons forming dark hydrogen atoms. The formation of bound states is always associated with dissipation of energy. You cannot form a bound state if you do not dissipate energy. So the easiest way to do this is to emit a dark photon. And then this dark photon, if it has a small mass, it can then decay into standard model particles via the kinetic mixing and give observable signals. So the radiative level transitions is a novel feature of these sort of models where you have sort of the possibility of forming bound states. Right?
Yeah. Why do you give the photon a mass? Do you have like a dark Higgs sector, or just somehow maybe it has a little mass?
So there are two ways to generate a mass, either via dark Higgs or via the so-called Stuckelberg mechanism. Now, if it doesn't have a mass, it's not going to decay into standard model particles. This is, of course, perfectly fine, right? But if it does have a mass, then there is this possibility. All right, so now the reason I went through this is not just to talk about this particular model, but because these features, in one way or another, multi-component dark matter, velocity-dependent cross-sections, and radiative level transitions are actually features of asymmetric dark matter models where dark matter couples to light force mediators. In one way or another, sometimes in more complicated ways than not, these features do show up, and they're very important for the phenomenology of these sort of models today. All right, so any questions on this? Okay, so let me now go on to the last production mechanism that I will discuss, which is freezing. What is freezing? Well, up to now we talked about dark matter that couples fairly significantly to other particles. But what if this is not the case? What if the couplings of dark matter to other particles are not zero, but they are very weak? Then what happens? Well, what happens is that dark matter is not necessarily in thermal equilibrium in the early universe. So I do not start from a large dark matter density early on. Can I still produce dark matter in the observed amount? Is this still possible? The answer is yes, because if dark matter has some small, but still not zero, couplings to other particles, then it may be produced in various decay and scattering processes that these other particles participate into. So there are various ways this can happen. You can have scattering processes of scattering of bath particles producing dark matter, or you can have decays, as I said. And these processes are described by Boltzmann equations, much like we described thermal freeze-out before. The first one is actually the same equation as what we had before. The second one is a bit different. You can have many different variations of this sort of freeze-in scenarios. Here, you can make the assumption that these parent particles, the psi particles here, are in thermal equilibrium, or maybe they have themselves gotten out of equilibrium when they produce dark matter. Maybe there is more than one kind of these bath particles that participates in these processes. There are many different variations of this sort of scenario you can do. But the important thing here is that the initial dark matter density is very small. So you do not start from a large dark matter density, because these interactions that produce dark matter are not very efficient. They produce dark matter, but it never reaches a very large density such that the inverse processes destroy dark matter efficiently. So this is the picture we have. Remember, before we started with dark matter being in equilibrium and then it froze out. Now what we have is that dark matter starts from a very low density or zero density, and then the density of dark matter starts building up, right? In contrast to the freeze-out mechanism, freeze-in has memory, so it matters where you start from, right? Now, what about candidates in this sort of production mechanism? Well, perhaps one of the most famous candidates produced by freeze-in is the sterile neutrinos. The sterile neutrinos are motivated by the observation of neutrino masses. We know that the neutrinos have mass, and to give mass to neutrinos, we have to introduce new degrees of freedom, new particles, right, that couple to the neutrinos of the Standard Model. So in the simplest scenario of neutrino mass generation, you have some right-hand neutrinos coupled to the lepton doublet and the Higgs by this operator. And these neutrinos are also, because they're a singlet under the Standard Model gauge group, they are also allowed to have Majorana masses. So if these Majorana masses are much larger than the mass terms generated after electroweak symmetry breaking via this term, then what happens is that you have a pattern of neutrino mass mixing that splits into two. On one hand, you can diagonalize the mass mixing matrix that comes out from this, and you have some light eigenstates that are a linear combination of the active neutrinos, a linear combination of the Standard Model neutrinos and the right-hand neutrinos, but they contain mostly Standard Model neutrinos, and they have this mass. And then you have another linear combination, which is mostly right-hand neutrinos that have a mass equal to the Majorana mass, right? And this is the mixing. Via this term, the eigenstates, the light eigenstates and the heavy eigenstates, they mix. They can oscillate into each other. It turns out that via oscillations from active neutrinos, you can produce these sterile species in the right amount to account for the dark matter of the universe if these sterile species have a mass of about a few keV and a mixing angle theta square of 10 to the minus 10. This is not the only way to produce sterile neutrino dark matter. You can extend the theory further, and you can, for example, couple the sterile neutrinos into a new scalar field that also couples to the Higgs. In this case, besides the oscillation production mechanism, you can also have sterile neutrinos, or indeed any other kind of sterile fermions, singlet fermions, produced via decays of these heavy particles. So this heavy scalar couples to the Higgs. It comes into thermal equilibrium in the early universe via this coupling, and then it can decay into sterile, into singlet fermions and produce them in the right abundance to account for dark matter. Right? Sterile neutrinos are an example of decaying dark matter. So because of this operator over here, the sterile neutrino can emit a photon and can decay into an active neutrino and a line photon. Right? This is a two-body decay, so this is a line photon. Right? The fact that it is decaying dark matter is part of what specifies this parameter range. So this decay process has to be slow enough such that the sterile neutrinos are long-lived, right? So the decay rate here depends on the mass of the sterile neutrinos and depends on the mixing angle. So both the mass and the mixing angle have to be small enough such that the sterile neutrino is cosmologically stable at cosmological scales. Nevertheless, this can give a detectable signature that people are looking for. Another candidate in this, this production mechanism is the gravitinos that appear in supersymmetric models, in particular in models where the supersymmetry breaking is mediated, gauge mediated. So as with the neutralinos that we discussed in the previous hour, the gravitinos would be stabilized by the R parity. And they would be produced via scatterings and decays of supersymmetric particles. Right? And then you can compute their density, and this is a fairly complex calculation that depends on various things. Right? All in all, to summarize the production mechanisms what we just discussed, within a given theory, basically, you have some couplings and you have the dark matter mass. And so within a given theory, you can calculate what couplings you need to obtain the observed dark matter density from thermal freeze-out. And you will get some solution over here. Couplings that are larger than this can still give you viable dark matter scenarios, provided that you have an asymmetry in the dark sector. And of course, to have an asymmetry, you need also a U1 low energy symmetry. Right? Couplings lower than that can give you viable scenarios if dark matter is produced non-thermally, and provided that you make sure that, well, it doesn't thermalize ever in the early universe, right? So this is sort of the picture you should have in mind, but what is important to remember also is that where exactly this line is depends on various cosmological assumptions, right? So it depends on the expansion rate of the universe, it depends on the reheating temperature, it depends on whether you have other cosmological events taking place, like some sudden entropy injection in the universe for some reason, or non-standard cosmologies, various things. Right? Any questions at this point?
Can we go to slide
71?
71.
You repeat the question?
He didn't ask it yet.
So you said freezing for the second case, so with the Higgs boson, S squared and H squared interaction. So it's a freezing before the electric restriction.
Freezing before what?
Freezing before the electronic phase transition.
Well, it depends on the precise mass of this guy and this coupling over here.
So the freeze-in happens.
So he was asking if the decay of dark matter, if the production of dark matter, so the decay of the S boson, happens before or after the electroweak phase transition.
So the freeze-in happens through that lambda coupling.
No, so this lambda coupling brings the S boson in equilibrium with the standard model. So then we know how many of these guys we have, right? And then the production of dark matter happens via this coupling. And in fact, there is a correlation of parameters here, because the rate at which dark matter is produced depends on this. So how much dark matter I will have depends on this. And at the same time, if this S boson acquires a VEV itself in the electroweak phase transition, then what happens is that this term also generates a mass, a Majorana mass, this Majorana mass, for the sterile neutrinos. And so now, how much dark matter I have today depends on the number density and on the mass, right? And this gives you a nice correlation of parameters. And it turns out that if this new boson lives at the electroweak scale, which so it has a mass of the order of, say, TeV, which you sort of want in order to not have a big hierarchy between the new scalar and the Higgs. So if this lives at the electroweak scale, then this coupling has to be such, in order to produce the right amount of dark matter, this dark matter has actually to be KV. This is nice because we didn't ask for it. And the KV range here is important because if the sterile neutrinos are much heavier than KV, then they would actually decay very quickly. So it's a nice interplay of parameters. Yeah.
But now that you have a new scalar, which is dark, does that also add to the dark matter?
It is unstable, so it decays. It decays into sterile neutrinos, but also it decays into standard model particles.
So if it decays into the Higgs, then that means maybe we could detect it with the LHC?
So I think can you
sorry,
the
yeah.
question?
So the first question was, so now we have also introduced yet another particle besides dark matter, this S boson. So wouldn't this also participate in the dark matter of the universe? And the answer is that it is unstable. So we use it to produce dark matter, but it doesn't survive until today. It decays into dark matter, but also decays into standard model particles. Now, can we see this S boson? Yes, we hope that through this coupling, and because through this coupling, this boson couples to the standard model fermions as well, one may hope that one can see it at the LHC. And this is something that people are looking for. Scalar extensions of the Higgs sector is something that, for many reasons, people are looking for. There are constraints and so on and so forth. Yeah.
So in terms of kind of producing structure in the universe and the distribution functions of velocity and stuff that you might get from these kind of production mechanisms, how unique are the predictions that these mechanisms have for observables that would be related to structure formation?
Right, so that's a very good question. So eventually I will learn it. So the question is, how are the production mechanisms related to the momentum distribution of dark matter, and how is this then related to structure formation? We know that the momentum distribution of dark matter affects structure formation. So. All right, so yes, this is a very good question. So to answer it specifically on these models, the scenario of production of sterile neutrino dark matter from oscillations was first proposed by Dodelson and Widrow This would be, so in the simplest implementation, so you can calculate the spectrum, the momentum distribution of dark matter, right? You can. So what you get from here is warm dark matter. It seems, so this is perhaps under investigation, but it seems that this production mechanism perhaps gives you dark matter that is a little bit too warm, or maybe yes.
Yeah, there are ways you can do this that actually make it cold.
Exactly.
Colder.
Exactly. So one way you can produce sterile neutrinos from oscillations and make them be colder is another mechanism which was produced by George Fuller, and in which you have, if you have a large lepton asymmetry while these oscillations are happening, then it turns out that the low energy spectrum of neutrinos is preferentially converted into sterile neutrinos, and therefore you get dark matter that is much colder, right? And this production mechanism over here also gives you colder dark matter than what the simplest oscillations give you, because what happens is that the decays of this guy happen early on in the universe above the QCD phase transition. And when the QCD phase transition happens, there is a lot of entropy release, which reheats the ordinary, well, which reheats the standard model, but dark matter is decoupled, so it doesn't get reheated. So dark matter becomes colder, and therefore you get sort of more cold dark matter. But just to wrap this up, this is important because the take-home message from this is that when we talk about warm dark matter is not just one scenario or one thing. How warm dark matter is actually depends on the production mechanism. So sometimes when people say warm dark matter, they have in mind some sort of thermal production mechanism. But from these mechanisms, for example, you get non-thermal dark matter, right? You can calculate the spectrum. So it is always important to keep in mind what production mechanism we refer to, right? All right. So, okay, and this is sort of almost the last part of this lecture. Interaction types. So we sort of already talked about different kinds of interactions that dark matter may have. Now, most of the dark matter research, in fact, has concentrated on one kind of interactions, which is contact type interactions. What are contact type interactions? Contact type interactions are interactions mediated by particles which are either heavier than dark matter or of the same order or not too much lighter, right? So, or the same order as dark matter, let's say. This is the case in the prototypical WIMP scenario, where WIMPs were hypothesized to have the same mass or a similar mass to the electroweak gauge bosons, right? The W and the Z, so 100 GeV, right? But now we can ask, what happens if dark matter is actually much heavier than the mediators to which it couples? How does the phenomenology of dark matter look like if this is the case? What changes in what we have already computed? Right? It turns out that there are some very interesting effects, non-perturbative effects, that arise in this regime. So I will be talking in particular about the so-called Sommerfeld effect and the formation of bound states. The reason these effects are important for the phenomenology of dark matter is because they change the rate of the various radiative processes that take place, and in fact they add new radiative processes that can happen, and they can affect the dark matter phenomenology. Before we discuss this any further, we first have to be motivated enough. Why do we care about interactions mediated by light particles, also known as long-range interactions? Well, we care about them for various reasons. One is the self-interacting dark matter scenario. Indeed, if dark matter is self-interacting, has to be self-interacting if we eventually converge in this, then the self-interactions may be mediated by light particles. More generally, there are hidden sector models that are inspired either by GATS or even string theory that have dark sectors where there is a dark sector with stable particles that couples to light force mediators, and these stable particles may have been produced in cosmologically significant abundances in the early universe. They may make up the dark matter of the universe today, and therefore we have to learn how the phenomenology of dark matter would work in these cases. Long-range interactions also appear in many models of the so-called designer dark matter, models that have been designed to explain the occasional astrophysical anomaly that pops up. Right? But what is quite interesting is, in fact, that even the weak interactions of the standard model, which have been the prototype of contact interactions in particle physics, even the weak interactions of the standard model manifest as long range if dark matter is heavier than a few TeV. Right? So long range, the phenomenology of long range interactions is important for TeV scale dark matter. And remember, the TeV scale for WIMP dark matter is well motivated because this is what we get in minimal models, right? It is not something irrelevant to WIMP dark matter. But in fact, long-range interactions are important for WIMP dark matter that co-annihilates with other colored or charged particles, like as it happens in various scenarios that people are interested in nowadays in the MSSM, where neutralinos can co-annihilate with stops. Right? Okay, so let's see what happens differently when we have long-range interactions. I will start first with contact type interactions and just review very briefly how the scattering processes work. How do we compute a scattering process when we have contact type interactions? Well, when we have contact type interactions, what we do is we say, well, we take our particles, we separate the asymptotic states from the interaction part. We take our particles to infinity. We say they do not interact anymore. They're essentially free particles. And then when they approach, they interact. And this interaction part is something we calculate with Feynman diagrams in the standard perturbation theory and so on forth. And, but we can also elaborate a little bit on what our asymptotic states look like. In principle, if we want to do a fancy calculation, what we can do is we can calculate the properties of the asymptotic states. The way we do that is by calculating these two-point functions, and we do that by resumming all one-particle irreducible graphs. Now, what we get from here is that the propagator of an asymptotic state looks like this. It has something that's called the field strength renormalization factor and something in the renormalized mass. What is the physical significance of this field strength renormalization factor and of the renormalized mass? Well, these parameters tell us how the asymptotic states of an interacting field theory differ from the asymptotic states of a free field theory. Right? Again, the way we calculate these parameters is by resumming the interactions of these particles, of this particle at infinity, the self-interactions of this particle at infinity. We resum the one-particle irreducible graphs, where, to remind you, the one-particle irreducible graphs are graphs like this. If I cut an internal line, I do not get a two-point function, right? So this is... Okay, so again, to calculate the properties of the asymptotic states, we calculate what the particles do at infinity. And if we have contact interactions, we calculate what each one of these particles does individually at infinity. Right? Fine. Now, these factors, we do not calculate them just for the sake of it, but once we calculate them, then they do appear in the transition amplitudes. So the amplitude for a scattering process will be the part that we calculate perturbatively over here, the interaction part, this A, but it will also contain these field strength renormalization factors. Right? Okay. Now let's say we have long-range interactions. if we have long-range interactions, we cannot take the particles to infinity and say they do not interact anymore, because we have long-range interactions. That's exactly what long-range interactions do. They make particles interact at very large distances. We cannot do what we did before anymore. So what do? How do we resolve this problem? Well, the problem is that we have to calculate again the properties of the asymptotic states. Before, we resummed the one particle irreducible diagrams. We resummed the interactions of each particle at infinity. Now, we have to resum the interactions of the two particles that interact at infinity. So how do we do that? Well, this is what we did before. Now, what we will consider instead of the 2-point function is the 4-point function. And instead of resumming the one particle irreducible graphs, we will resum the two particle irreducible graphs. Right? And just as an example, two particle irreducible graphs are again graphs which, if you cut an internal line, you do not get a 4-point function anymore. Right? So diagrams like this, for example. Right? So what do we get from this computation? Well, we will get some factors. Much like we had these field strength renormalization factors, we will get some other factors over here which will affect our transition amplitude for any process we may care to calculate. Right? In fact, much like before, in this case, in the 2-point function, these factors multiply the singularity, right? Multiply the pole we have, which corresponds to the asymptotic state, the particle we care about. These factors will also, here, in the case of 4-point function, these factors will multiply the singularities of the 4-point function. Right? How do we find these factors? Well, we find them by solving this equation, which is a Dyson-Schwinger equation. Right? So we resum this, we get an iterative equation for the 4-point function, much like here, we got an iterative equation for the 2-point function. So this Dyson equation for the 4-point function actually reduces to the Schrödinger in the non-relativistic regime. After you do some approximations, this equation for the 4-point function reduces to the Schrödinger equation for these factors, these wave functions, or field strength renormalization factors, you can call them as you like. It reduces to the Schrödinger equation for these wave functions, the familiar Schrödinger equation. This is how you get the Schrödinger equation in QFT. Right? Because remember that the 4-point function contains these wave functions. Right? It is essentially the residue of the singularity that you have here, much like these factors are the residues of the singularity you have in the 2-point function. Right? So this is what the wave function is. So we can find out these wave functions from the Dyson equation or the Schrödinger equation once we specify the potential, or once we specify the kernel of the two-particle irreducible interaction. Right? And we can do so in our desired order of perturbation theory. Right? Okay, now you see there is some difference between these wave functions here and these factors over here. In particular, there are some extra symbols. What are these symbols? What do they stand for? Well, because now we have two particles instead of one, there is an internal degree of freedom, which is the relative momentum. So this argument here, the wave function comes with an argument, which is the relative momentum of these two guys. And there is also a quantum number. There is another little symbol over here, this k, which is a quantum number that characterizes a particular state, and it is the expectation value of the relative momentum. So if I turn off the long-range interaction, what happens is that these two particles are two plane waves, which I can rewrite in terms of a plane wave that describes the total motion and a plane wave that describes the relative motion. Right? So then if I turn off the long-range interaction, this wave function is simply a delta function, which tells me that the relative momentum is exactly this number, this quantum number. So I have a plane wave. Now, if I turn on the long-range interaction, what happens is that this wave function is not a plane wave anymore. This wave function is not a delta function in momentum space, and in coordinate space, the wave function is not a plane wave. The long-range interaction distorts the initial, the asymptotic state wave packet, and this affects the amplitude of any process we may hope to calculate. Okay, but what we care about is the phenomenological implications for dark matter. So let's have a look at what happens. I will start doing so in the context of a very simple scenario, dark QED, just to keep everything simple. So remember, we saw this diagram before, dark matter annihilating into dark photons. If you calculate this process perturbatively to lowest order in the non-relativistic regime, the annihilation cross-section times relative velocity is this thing. It's a constant. Right? But now, if the dark photons are massless or light enough, then, as we just said, what we have to do is resum the interaction of the two particles, these two particles at infinity. So remember that what we were doing is we were adding up an infinite number of two-particle irreducible graphs. The lowest order two-particle irreducible diagram is the one boson exchange. If I add it infinite times, this is the sort of diagram I get. This is also known as the ladder diagram. So by taking this into account, the amplitude, now remember, is not just the perturbative part, but also it contains this wave function. So the cross-section, it ends up being, to lowest order, this perturbative cross-section I calculated here times a factor, where this factor is the wave function evaluated in coordinate space at r equals 0. Right? You can calculate it analytically if you have a Coulomb potential. So if the mediator is massless, you can calculate this analytically, and it ends up being this factor over here. It depends on the ratio of alpha over v, the relative velocity. At large velocities, in the sort of, as you go towards perhaps the relativistic regime, at large velocities, this factor is 1. So you recover the perturbative result. But at low velocities, lower than the coupling alpha, what happens is that this factor S grows as alpha over V. So you can plot this. This is what you have here, the S factor, the so-called Sommerfeld enhancement factor, as a function of alpha over V. And you see that the cross-section is enhanced with respect to the perturbative value. Cosmologically, the reason I plotted this in terms of alpha over V, cosmological time goes this way, right? So the average alpha over V, the thermally averaged alpha over V is something that increases with time, right? Okay, but this is actually not the only thing that happens. Let's go back to the Dyson-Schwinger equation for a Coulomb potential. This is how it looks like. We have an equation for the 4-point function. This is what we solve. Remember that the 4-point function is these wave functions over the singularity. It turns out that there are two kinds of singularities that appear in this 4-point function. There are the singularities which are characterized by wave functions, by a continuous spectrum. These wave functions, where k is a continuous variable starting from 0 and going to something large, whatever. These states to which the states described by this continuous spectrum have energy which is larger than the sum of the masses of these two particles. So they have positive energy. But besides this, which is what we used before, there is a discrete spectrum. We can have another kind of singularity over here. We can have poles. The discrete spectrum corresponds to energies that are less than the sum of the masses of the two interacting particles. So negative energy states in that sense. They are described, these states are described by some wave functions which have quantum numbers, discrete quantum numbers. So what is k? The role of k over here is played by the discrete quantum number n over here. So here you have a momentum that is not quantized, it is continuous. We have a continuous spectrum. Here we have a momentum that is quantized, right? Okay, so these states are bound states, right? So they have energy, again, less than the sum of the two masses. If bound states exist, bound states can form. How do bound states form? As we said before, bound states can form only if you dissipate energy, and otherwise they cannot. The easiest way for our applications to dissipate energy is to emit something, to emit a light mediator. So these are the diagrams we have here. The initial scattering state of two unbound particles that interact at infinity comes together, they emit a dark photon, and they get captured into a bound state. So both the scattering state and the bound state are described by a ladder diagram, but these ladder diagrams, these 4-point functions, are evaluated at a different energy, right? Now the amplitude for this process, in analogy to what we had before, will depend on the will contain the perturbative part, which is this radiative vertex, and will be convoluted with the initial state wave function, but also now with the final state wave function, right? So it's a bit more complicated. Before we didn't have a bound state in the annihilation process. We didn't have a bound state in the final, in the right-hand side of the diagram. So we had only the initial state wave function. Now we have the final state wave function as well. So you can calculate the cross-section, the amplitude and the cross-section for this process. And for a Coulomb potential, you can get again an analytical solution. This is it. So you get, it factors out into something. You can factor out this part, which is equal to the annihilation cross-section, times this factor, which again depends on alpha over v. So I have plotted the two processes here, these S factors for the two processes, the annihilation process and the bound state formation process, as functions of alpha over v. And what you see here is that in the regime where the Sommerfeld effect becomes important, so when alpha over v becomes of order 1 or larger, in this regime, the formation of bound states is actually faster than annihilation. Bound state formation is actually the dominant inelastic process. Why is any of this important for our applications for dark matter? Because the formation of bound states can do many things. Among else, it can actually contribute to the self-destruction of dark matter. So in this simple model we have here, dark matter can annihilate directly into radiation, but it can also form bound states radiatively, and the bound states can then decay into dark photons. And in this way, dark matter is depleted by yet another channel, right? So you can recalculate the coupling you need to obtain the correct dark matter abundance. So this is alpha as a function of the mass, the dark matter mass. The dotted line is what you get if you just do the perturbative calculation. The dashed line is what you get if you take into account the Sommerfeld enhancement of the annihilation processes. So you see that the Sommerfeld effect enhances the cross-section, therefore we need a smaller coupling to obtain the correct relic density. And if you now add the formation and decay of bound states, you get an even smaller coupling. Yeah.
Kallia, we're coming up on the break time, so maybe kind of wrap it up in 5 minutes.
Yeah, I will. Okay. Why is this important? Well, we care to calculate this coupling accurately because this coupling is what what determines all of the phenomenology of dark matter today. This coupling is what gets into the indirect detection cross-sections, the direct detection, so on, right? So we need to predict this coupling accurately. This is why we care about all of this. And what is interesting to observe here again is another manifestation of the fact that the early universe tames the late-time dark matter interactions, right? So by the Sommerfeld effect and the formation of bound states, which is also a Sommerfeld enhanced process as we saw, what happens is that the predicted coupling is smaller than we would have otherwise calculated. So again, this regulates the interactions of dark matter today. Now, what I described up to now was about massless mediators. What happens if mediators are not massless, but just they have some mass? Well, in this case, there are 3 scales that are relevant to the problem. One is the average momentum transfer in the non-relativistic scattering processes, which is the reduced mass of the 2 interacting particles times the relative velocity. The other one is the Bohr momentum, or the inverse Bohr momentum, which is the Bohr radius, mu times alpha. And the other one is the mediator mass, which determines the range of the potential. When we have massless mediators, we saw that the only parameter that is important is the ratio of these 2 scales, the average momentum transfer and the Bohr momentum. This is what this zeta parameter was about. It was not alpha over v, it was mu alpha over mu v, right? And the Sommerfeld effect and non-perturbative effects appear when zeta is of order 1 or larger. Now we will have one extra parameter, which will be the comparison between the Bohr momentum and the mediator mass. So non-perturbative effects appear when this parameter is larger than 1. So when the range of the potential, which is the inverse, mass of the mediator, when the range of the potential is larger than the Bohr radius. Right? So this answers the question, how light is light? Light is when this parameter is of order 1 or larger. And this is actually when you have a Yukawa potential, this is when bound states also appear. Right? Okay, now I want to warn you that in recent, even quite recent literature, there is a confusion, there has been a confusion, because when you have a massive mediator, the scattering state wave function exhibits parametric resonances that are associated with the existence of bound states. For a very long time, people confused these resonances with the formation of bound states. These are two different things. The resonances the resonance may be described as the formation of zero energy bound states. They are not the formation of actual bound states. These two processes are the formation of actual above threshold bound states is a very different process than the resonances that people observe in annihilation cross-sections. Right? Okay, now all of this is not just interesting for hidden sector models, but is also interesting for WIMP models. So we said before the electroweak gauge bosons have for a very long time been considered heavy, but if we now start talking about TV scale dark matter, then in fact the electroweak interactions manifest as long range. Indeed, you can calculate this parameter for the electroweak interactions, and you will see that this parameter becomes of order 1 if the dark matter mass is of order of TeV. Because WIMPs belong to non-abelian multiplets, the whole situation is quite more complicated than what I showed before with in the U1 model. Here you have, for every the components of the multiplet interact in different ways. So for example, the neutral components can exchange a W and become charged, and then the charged components can exchange Zs and gammas. So somehow you have to take all these interactions into account and build a sort of potential matrix and to calculate this correctly. And here is the result from freeze out. If you have, so if you have a SU2 triplet, which is also like what you have when you have window dark matter in SUSY models, you can compute the relic density as a function of the mass. This is what you get if you take into account only the perturbative annihilation. So then you would find out that the mass would have to be around here. But if you take into account the non-perturbative effects, the Sommerfeld enhancement, you see that the annihilation is enhanced, and therefore you get the correct relic density for a larger mass. The effect is even more spectacular if you have a higher multiplicity dark matter in a higher multiplicity state, so a quintuplet. Over here, the difference between the two mass determinations is much greater. All right, so here I just showed the importance of long-range interactions for the relic density, but long-range interactions can affect also other aspects of dark matter phenomenology, indirect detection, and the self-interactions inside halos. And
Go ahead. We can delay 10 minutes or something.
This is, I just have one.
Just 1 minute.
All right.
Yeah.
I just have one more slide.
Okay.
All right. So with this, just this slide to just sum up what are some interesting, perhaps interesting topics in the current dark matter research. This is a very partial list, and also it maybe reflect my own interests more than anything else. So we talked about galactic structure in the beginning. It is important to improve our observations and understand better how structure forms at small scales. So this goes back to a question that was asked. It is important also to improve our simulations. There is a lot to be done along this direction. On the theory side, it's important to understand what our models predict. We saw before that many self-interacting dark matter models predict multi-component dark matter, and there are many complications in this respect. So we have to compute these things better so that we can offer them as input to simulations, right? There is a lot of recent interest in light dark matter, and there are, in fact, a lot of experiments, new technologies that are being developed to detect light dark matter. From the theory point of view, we need to consolidate the motivation for light dark matter. Asymmetric dark matter provides some motivation for that. We need perhaps to come up with benchmark models and compute what sort of interaction strength we expect. Another direction in dark matter research currently is, well, the opposite side of the spectrum, heavy dark matter, heavy meaning heavier than a few TeV. Right? There are many new experiments that have either started or will start. IceCube, CTA, and HAWK, they probe the multi-TeV regime or PeV regime. So they offer a new window into a heavy dark matter. We just talked about, however, how for heavy dark matter there are new things we need to compute. There are non-perturbative effects that become important, radiative transitions which can give rise to new signals, as we saw. And in fact, another thing that we didn't talk very much about is the role of substructure, right? Because these non-perturbative effects actually become even more enhanced when you have rich substructure, and somehow you have rich substructure when you have heavy dark matter. So somehow there is a correlation there that needs to be explored in more detail. Another aspect of current interest is a metastable mediator. So if you have some sort of hidden sector, then what happens? The mediators to which dark matter couples in this hidden sector may also couple to the standard model. We saw an example before. If you have, and they may decay into a standard model, this may give rise to displaced vertices in colliders, but also it can give rise to, or it can, to indirect detection signals. And finally, something else that has become of, has attracted a lot of interest recently with the LIGO results is primordial black holes, and likely there will be a lecture on this separately. Okay, and with that I will stop. Thank you very much.